Hi there, welcome to your lesson on geometric sequences. Specifically, we're going to be looking at the nth term of a geometric sequence, the first formula for these sequences. Let's begin. This is a very big idea. As we saw last time, arithmetic sequences are one main type, and this is another big type of sequence. Let's take a look. Let's begin with a little bit of a flashback, and just like last time, what you're going to see may be review of things you've seen before, so don't worry about writing this down. Let's just listen. So there are two types of important sequences. Once again, arithmetic we looked at last time. This time let's look at geometric sequences. These are sequences with a common ratio. Remember, arithmetic had a common difference. Geometric have a common ratio between successive terms. Alright, so let's look at these here. We have a sequence that begins 40, 20, 10. That one, if it was arithmetic, remember, we would be adding or subtracting the same number, but here we see this is minus 20 and then minus 10, so it's not a common difference. But we can look at that 40 and say, oh, 40 times 0.5 gives us 20, or in other words, half of 40, or 20 times 0.5 gives us 10. So now we have a common multiplier, and that is what is called a common ratio. So if you continue the pattern here, half of 10 is 5, half of 5 is 2.5, half of that is 1.25. That is now a geometric sequence. It has a common multiplier, which is known as a common ratio. We're going to use the letter R. And the way to find the common ratio, just like we found the common difference by taking like u2 minus u1, so taking the next one and subtracting the previous, now to find the common ratio, we're going to take the next one and divide it by the previous. So when you divide 20 by 40, you get 0.5, our common ratio. Or if you divided 10 by 20, you would get 0.5, our common ratio. Let's look at the next one. This one's a little tougher to see maybe, but again, if you try the rule of dividing this one by the previous one, or this one by the previous one, we should be able to get the common ratio. In this case, you may have noticed that to get from root 6 to 6, you can multiply root 6 by root 6. Because when you multiply a root of something by the same root, you end up with the roots canceling each other and just what's inside the root. So again, root 6 times root 6 gives us 6. Now do that 6 times root 6, well, there we have it, 6 times root 6. Now multiply this by root 6, well, the two root 6's again will cancel, leaving only a 6, so you'll end up having 6 times 6, which is 36. Okay, and then that times root 6, well, 36 root 6. Then this times root 6, again, you're going to have another root 6 multiplying this, so those two roots will cancel, and you'll be left with a 6. So 6 times 36 is 216. So I hope that makes sense. You have to have a little bit of background with the roots to see how that works. Now let's check how we can get the ratio. Again, you can take one term and divide it by the previous. There's our common ratio. And that equals root 6. If you remember, when you have a fraction like this with a root on the bottom, you can rationalize the denominator, means multiply the top and bottom by root 6. And again, that will give you 6 root 6 on top, and on the bottom, root 6 times root 6 will be just 6. So the 6, let's see, the two 6's will cancel, and you're left with root 6. And that is our common multiplier here. Okay, so we're going to plot these points and see what happens. So we have a geometric ratio here as well. I see 3 turning into a 6, so times 2. 6 turning into 12, times 2 again, times 2, times 2, times 2. So there's our pattern, clearly established, multiplying by 2. Therefore, it's a common multiplier, therefore that is our common ratio. So we have a geometric sequence. Let's plot the points. First term, position number 1, we have 3. Position 2, we have a 6. At position 3, we have a 12. At position 4, we have 24. At position 5, we have 48. And at position 6, we have 96. Notice, remember, we had with arithmetic, they made a linear, they lined up in a line, right? But in this case, it's not. There's a curve to it. It's curving up. So geometric sequences are always exponential. This is exponential growth happening right here. So geometric, always exponential. Because that multiplier basically makes it grow slowly, not slowly, makes it grow and then grow quicker, quicker, quicker as we're multiplying bigger numbers by the same multiplier. Alright, which of these are geometric? First one, yes or no? First one, well, it is. We see a common ratio of 3, common multiplier of 3, geometric. Next one. Multiply by 3.5 multiplied by 1.7, no common ratio, not geometric. And to get that 3.5 again, you could have done 7 divided by 2, you get that multiplier. Then 12 divided by 7, you get that multiplier. So always divide the next one by the previous one to see what the multiplier is. Last one, yes or no? Well, it is. This time we're multiplying by 1/3. And then multiply 1/3 again to get 9. And 1/3 of 9 is 3. And 1/3 of 3 is 1. So multiply by 1/3 all the way. And there's our common ratio. Again, you could have gotten that ratio by saying 27/81 and reducing that to 1/3. Or 9/27, and that would be reduced to 1/3 as well. So that's our common ratio. Let's take some notes now. So we've looked at just a recap of things you may have seen, and now let's go a little deeper with these and let's take some notes. So geometric sequences. Sequences that have a common ratio or multiplier are called geometric. So that's kind of summarizing what we've talked about. Next, to find the common ratio, again, you take the next term and divide it by the previous term, and that's what this means. Un plus 1 is the term that follows un, right? Because the n value has grown by 1. So the next term divided by the previous. Okay, geometric sequences. There are two main types. Let's take a look. One is called a diverging sequence, and this is an example of one of those. What do you notice happening with these numbers here as you proceed? Well, they're growing, right? The multiplier is 4 times 4 times 4. So when the multiplier makes the sequence numbers grow, it is called a diverging sequence. So in this case, the multiplier was 4, or the ratio was 4. And basically, what that means is anytime the ratio is greater than 1, it's going to make these grow, right? Because you're multiplying by a number greater than 1, these will grow in value. And also, if you're multiplying by a number less than -1, in other words, let's say like -2. If you're multiplying this by -2, it would be growing. Of course, it would be becoming a larger negative number, but it's still becoming a larger number. That's the key here. So those are diverging sequences. Converging sequences, as you may imagine, are when they do the opposite. When you look at the sequence, the numbers decrease. For example, this one here. We have 6, then -3, then 1.5, and then it gets smaller, smaller, smaller. Here it goes from positive to negative, but again, that's not important. It's not whether it's positive or negative, it's whether the actual value here is decreasing, and those numbers are decreasing. In this case, the multiplier is -0.5. You multiply, it becomes half of what it was, but also becomes negative, right? So negative half of 6 is -3, and then you multiply by half again, and a negative, and it turns negative into a positive. So the next one will be negative again. So that is a converging sequence, and that occurs when the r value, the multiplier, the ratio, is between -1 and 1. So think of it this way. The only way a number can get smaller when you multiply it by something is if the number you're multiplying it by is under 1, right? Because if you multiplied 6 by 1, it would remain a 6. If you multiply 6 by anything greater than 1, it will grow in size. But if you multiply 6 by something less than 1, it will shrink in size. So that's exactly what's happening here. The multiplier is between 1 and -1, and that means it can be like a number between 0 and 1, which is again a number smaller than 1, or it can be a number between 0 and -1, which is a negative number which is smaller than 1. Okay, let's move on from there. So we're going to do a quick investigation to see if we can pull out the rule for geometric sequences. Again, we did a similar thing with arithmetic sequences, but let's do it here again with geometric. So first, look at this sequence here. We have 24, 12, 6, 3. Hopefully it's obvious what's happening there, right? We're basically, again, multiplying by 0.5 or by 1/2, right? Multiplying by a half every time. So the number is becoming half of what it was. So our r value is 0.5. Now what I'd like you to do is write a recursive rule. So again, we're going to go back to recursive rules for a moment, not explicit, but recursive. A rule using a rule for u2, which uses r and u1. So you're making this recursive rule that has r and u1 in it, and again it's going to be u sub 2 equals something something. So imagine, how do you get this number from this one? What would that rule look like? Here we are, u sub 2 equals u1. So again, a recursive rule is a rule where we need to know the previous term to figure out what the next term will be. So the next term, u2, you begin with u1 and you multiply it by the ratio. That makes sense. To get to here, you begin here, you multiply it once by that ratio, and then you get the second term. So the second term is produced by multiplying the first term by the ratio. Okay, let's try again here. So write a recursive rule for u sub 3 using r and u1. So just like with the arithmetic, remember we're using u1 in this rule, not u2. If we're using u2 in this rule, well, that would be simple. To get u3, we just take u2 and multiply by the ratio, right? But here we want to use r and u1 in the rule, so try it out. Well, here's that rule. To get u3, we can begin at u1 and multiply by r squared. And r squared just means multiply by r and multiply by r again. So that makes sense. Let's take a look. To get to the third term, we can begin at u1. So we begin at the first term, we multiply by r once, we multiply by r again. So we multiply by r twice. So to go from the first to the third, we have multiplied by r twice. Okay, let's keep going. Now repeat the rule, or repeat the process for u sub 4. There we have it, alright, so u sub 4 equals u1 times r to the third. That means multiplying by r 3 times, right? So again, to get to the fourth term, we start the first one, we multiply by r once, multiply by r twice, multiply by r 3 times. So that's what we have here. So finally, looking at the clear pattern going on there, generalize a rule for u sub n. What will that rule look like now for u sub n? So now we're not using 4 and 1 here, we're using u sub n. What does it equal? And keep u1 in the rule, and then see if you can deal with the exponent. So here is our rule. To get any term in the sequence, we take the first term and we multiply by r, and the number of times we multiply by r is n minus 1. And you can see that from here, for example. To get the fourth term, we start with u1, we multiply by the ratio 3 times. This number here is always going to be 1 less than this number. And you can see it here also. To get u3, we start at u1, multiply by the r ratio twice. Again, this number is always 1 less than this one. And that's why we have n minus 1. And the reason it's 1 less is because if we go from u1 to the third term, for example, to go from 1 to 3, there are 2 jumps, or 2 multiplications of r, so 2 jumps there. Okay, so that's our general rule. Key rule, that is our main rule to begin geometric sequences. And let's put it in here one more time. There's the rule. And let's see if you can just solve this problem here. Now that we have this rule established, look at this one here. It is definitely geometric. Find the 8th term using the rule here. Okay, so here we go. We write the general rule. U sub n equals u1. We can see u1 is 24 times 0.5. Our ratio here is multiplying by half every time, n minus 1. Now, that's the general rule, but we want to find the 8th term, so now we replace this with 8 and this with 8. So u sub 8 equals 24 times 0.5 to the 8 minus 1, and then that can be written as 24 times 0.5 to the 7th power. Again, we need 8th term, therefore we see a 7 here, always 1 less. Put this on your calculator. All this can be done on the calculator, right? 0.5 to the 7th power. You can use that little symbol that looks like a little, I don't know what it's called. It looks like a triangle without a bottom. That symbol can get you exponents on your calculator. Multiply that and you should get this answer here. Alright, so I think we'll leave this video here. This has been an introduction. We've derived the formula. We've kind of explained the idea of geometric sequences. There is a second part. It looks like commonly there'll be 2 videos for these lessons. The second video will then get you into a bunch of practice problems so you can really see if you can apply this particularly to some tougher problems. So don't quit yet. End this one and see you very soon in the next video. Get to that one right away.